Hi, this is Darren Fleischer. And I'm Zachary Goldman. We're going to be presenting on distributed cognition and PISA math scores. Our interest in this specific research came about because there are gaps in the literature around the large-scale effects of the distribution of cognition between individuals and tools, and the potential effects this has on student math achievement. This distribution of cognition, otherwise known as DCOG, may have many significant positive effects on student achievement in mathematics. Our contention is that having access to a distributed cognitive system expands one's cognitive abilities, more than simply working on one's own and having access to known tools. Our research question is the following: does access to distributed cognitive systems in schools significantly relate to math achievement?
Data for this study came from the 2012 PISA mathematics test, as well as student-level and school-level surveys. We studied 1,951 students within 147 U.S. schools participating in the 2012 PISA. The model for this study includes the following variables: our outcome variable, which is based on the PISA math achievement scores for individual students; our level 1 independent variables, which include X1, student group work perception. This variable is based on student self-reporting, whether or not they work in groups for math. X2, math participation outside of class, is another student level variable, which is an aggregate of student responses around joining math and chess clubs, doing math work at home, and discussing math work with their peers. Our W1 is math computer policy, a dichotomous variable, which represents whether the math department has a policy around using computers, and our W2 is the ratio of computers per student in the math class. Both level 2 variables were reported by the school. For our model, we look at a number of single variable impacts, as well as interaction effects of level 2 factors onto level 1 factors. Here we illustrate the school's math computers policy having an effect on whether students work in groups, their participation in math outside the classroom, as well as the outcome variable's math score. The same holds for ratio of computers on the level 1 variables and our outcome variable.
In our research, we expect that access to a distributed cognitive system where someone can offload cognition onto tools or other members of the system has a significant positive effect on math achievement in the PISA 2012 mathematics exam.
Based on literature around technology and student habits involving learning math, as well as assumptions made around distributed cognitive systems, we expect to reject each of the following null hypotheses, barring H sub 01, which is simply the intercept with the intercept. Further, we surmise that we will reject the null hypothesis for every combination of level 2 interaction effects on level 1 variables and the outcome variable.
We notice the following limitations within our study. Missing data is one of them. We began with the sample size of roughly 4,700 participants, and after deletion, we're left with just underneath 2,000. Data was removed due to incomplete answers or missing information, which may add bias due to endogenous factors for not completing the survey questions in the first place. Thus, we have to be cautious with our interpretations of data and our conclusions. Also, there is a potential for confounding in that there are numerous variables within the PISA dataset that could explain PISA math achievement.